Quantum computing is no longer a far-off fantasy confined to the labs of theoretical physics. It's unfolding right now. From Google's Sycamore to IBM's Eagle, quantum processors are rapidly advancing, and they're about to change everything we thought we knew about computation. This is more than an upgrade. It's a full-scale paradigm shift that will reshape industries, science, medicine, finance, and even how we think about information itself. Imagine a computer that doesn't just calculate faster, it processes reality at a deeper level. Quantum computers use qubits, quantum bits, which can exist in multiple states at once, thanks to a phenomenon called superposition. But that's not all. These qubits can also be entangled, meaning their states are connected no matter how far apart they are. When you combine superposition and entanglement, you get exponential computing power. Not linear, not logarithmic, exponential. Let's compare. A classical computer solving a complex problem might take thousands of years. A quantum computer? Minutes. That's not science fiction. It's the foundation being laid today by giants like Google, IBM, Intel, and D-Wave. In fact, Google claimed quantum supremacy in 2019 when its 53-qubit Sycamore processor solved a problem in 200 seconds that would have taken the world's fastest supercomputer over 10,000 years. But what does this mean for us? Let's break it down, because this tech is about to touch every part of life. In pharmaceuticals, quantum computing is being used to simulate molecular interactions down to the quantum level. Traditional computers struggle with complex molecules because of the sheer number of variables involved. Quantum processors, on the other hand, can analyze these interactions in a way that could fast-track the discovery of life-saving drugs, including treatments for cancer, Alzheimer's, antibiotic resistance, and even rare genetic disorders. Drug development that used to take a decade could be condensed into just a few years. Startups like Protein Core and big players like Roche are already experimenting with quantum chemistry platforms to simulate protein folding, enzyme reactions, and atomic behavior. And beyond drug development, quantum sensors could be used for early disease detection, measuring changes at the cellular or even subatomic level long before symptoms emerge. In climate science, quantum simulations can model entire planetary systems with more variables and greater precision than ever before. That means better predictions, faster analysis of weather patterns, and even improved models for sustainability and renewable energy optimization. Imagine a future where energy grids are balanced in real time, where materials for solar panels and batteries are perfected using quantum materials research, where food security is enhanced through precise climate modeling that can account for everything from soil chemistry to atmospheric shifts to migratory patterns. This isn't just theory. The Department of Energy in the US is already funding quantum projects that aim to improve energy efficiency, battery performance, and carbon capture methods using quantum simulation techniques. Finance is another domain bracing for quantum transformation. Traditional algorithms hit a wall when it comes to predicting markets with high volatility and massive data streams. Quantum computing introduces a new class of optimization problems. Think portfolio balancing, fraud detection, and risk analysis performed in seconds instead of hours. In 2022, Goldman Sachs began exploring quantum algorithms for pricing financial derivatives, a notoriously complex task that could be made efficient with quantum advantage. JP Morgan Chase, HSBC, and BBVA have also launched quantum R&D labs to explore trading models and market simulation. Quantum computing could also enhance financial security, enabling better fraud detection by identifying anomalies in massive transaction datasets in real time, a task that overwhelms classical systems. Cybersecurity may be one of the most disrupted fields. Today's encryption methods, RSA, ECC, rely on the fact that classical computers can't easily factor large prime numbers. But quantum computers can. With Shor's algorithm, quantum systems could theoretically break RSA encryption in minutes. That's why post-quantum cryptography is already being developed by agencies like NIST, the National Institute of Standards and Technology, to secure communications before quantum decryption becomes a threat. But there's a flip side. Quantum technology also enables quantum key distribution, which creates encryption keys so secure that any attempt to intercept them destroys the message itself. China's Messias satellite has already demonstrated this over 1,200 kilometers using entangled photons. So while quantum threatens current cybersecurity, it also offers a path to next-generation defenses, ones built from the laws of physics, not just clever algorithms. And then there's AI. Artificial intelligence is already reshaping industries. but quantum computing could supercharge it. Quantum machine learning is the fusion of quantum algorithms with classical AI models. It could allow us to train complex neural networks using exponentially fewer resources and run models that are currently impossible due to hardware limitations. Companies like Xanadu, Rigetti, and IonQ are building hybrid quantum classical systems to run machine learning models more efficiently. These models are being tested in image recognition, language processing, and even quantum neural networks that learn from entangled data states. The implications? Smarter AI, faster AI, more interpretable AI, and possibly more human-like AI. So how close are we really? Right now, quantum computers are still in their infancy. Most systems are noisy, unstable, and require near-zero temperatures to operate. Quantum error correction is one of the major hurdles. Since quantum states are so delicate, even a single photon or vibration can cause decoherence and destroy a calculation. Yet that hasn't stopped progress. IBM's quantum roadmap plans for a 1,000-plus qubit system, Condor, and a 10,000-plus qubit system named Kookaburra by the end of the decade. Microsoft is pursuing topological qubits, which may be more stable, while companies like PsiQuantum are betting on photonic quantum computers to scale more easily, using light instead of matter. Meanwhile, startups are experimenting with trapped ions, superconducting circuits, and quantum dots, each with their own trade-offs in terms of speed, coherence time, and scalability. The point is, there's a race happening, and it's not just about more qubits. It's about better qubits, more stable, more connected, more accurate, and more accessible. There's even talk of a quantum internet. This network would use quantum entanglement and quantum key distribution to create unhackable communications and instant information transfer over long distances. In 2020, China demonstrated the first satellite-based quantum communication link. In 2022, researchers at Caltech and Fermilab announced a prototype of a quantum internet node. And in the Netherlands, scientists at QTech achieved entanglement-based data teleportation between quantum processors. The idea? Build an entirely new internet. One that can't be hacked, can't be cloned, and can't be tampered with. So, when will quantum computing enter everyday life? The short answer, sooner than you think. Right now, companies like Amazon, Google, and IBM offer quantum-as-a-service platforms like Amazon Breakit, Google Quantum AI, and IBM Quantum, where developers can run quantum programs on real hardware through the cloud. This opens up experimentation to researchers, startups, and universities around the world. Startups like Zapata, QCware, and Cambridge Quantum are building quantum-ready software platforms to solve real-world problems, from chemical simulations to traffic routing and logistics optimization. You may not use a quantum processor directly today, but your banking app, climate forecast, or AI assistant might benefit from one sooner than you realize. Governments aren't standing still either. The US has invested over $1.2 billion through the National Quantum Initiative Act. The EU's quantum flagship program is funding over 20 large-scale research projects. China, Japan, Canada, and the UK are all pouring billions into quantum tech, building national labs, military applications, and public-private partnerships. It's a new kind of space race, but instead of rockets, it's about who can first master the building blocks of reality itself. And the workforce is starting to respond. Universities like MIT, Stanford, ETH Zurich, and University of Waterloo now offer quantum computing degrees. There's even a growing movement to teach quantum coding in high schools, preparing the next generation for a quantum future. Still, quantum computing won't replace classical computers, it will work alongside them. Just as GPUs revolutionized AI training, quantum processors will serve as accelerators for tasks that demand extreme parallelism and complexity. Think of it as a new layer in the computing stack, a layer that adds depth, nuance, and possibility. For some problems, classical is enough. For others, only quantum will do. Together, they form a hybrid future, where the strengths of both systems are harnessed to push the limits of what's possible. Now let's address the skepticism. There are critics who argue that quantum computing is overhyped. They point to the challenges of scaling, the noise levels, the lack of widespread commercial use cases. And yes, today's quantum computers can't solve every problem better than classical ones. But remember, classical computing was once doubted too. The first electronic computers filled entire rooms, required teams of engineers, and had less processing power than a smartwatch. Yet they launched the digital age. Quantum computing is on the same trajectory, and it's accelerating. So what will this future look like? Imagine running a search engine that doesn't just find keywords, but understands context with quantum natural language processing. Picture a wearable medical scanner that reads your body's energy states using quantum sensors. Visualize autonomous vehicles with quantum-optimized pathfinding in real time, even in chaotic urban environments. Even more mind-bending, quantum computing could become a foundational technology for exploring consciousness, simulating complex brains, or decoding the mysteries of quantum biology, like how birds navigate using Earth's magnetic field, or how photosynthesis achieves near-perfect efficiency. This isn't just computing, it's a new lens for understanding the universe. And while we still face engineering roadblocks, the momentum is undeniable. Quantum processors are improving, algorithms are evolving, the ecosystem is growing. And for those paying attention, the future is already unfolding. So as you hear the buzz around AI, blockchain, and biotech, remember that quantum computing may be the silent revolution that unlocks them all. The next leap in technology won't just be faster, it will be stranger, more powerful, and far more transformative than anything we've built before. Because once we harness the rules of quantum mechanics, the very fabric of reality, we're not just computing, we're rewriting the code of existence itself. Want to stay ahead of the AI curve? Hit subscribe and turn on notifications. We break the silence around future tech, one myth at a time. This is Tech Mythos.